In this segment, we'll continue our look at the example list struct, and we'll introduce several other C language concepts related to larger code. Let's start with the enum declaration on line 12 of list.h here. It's often useful to use integer values to represent one of several choices from a set. Examples might include the days of the week or one of a set of possible colors. If we need to store, say, a day of the week in a C variable, the standard approach is to assign a number to each day, usually starting with 0, so perhaps Monday is 0, Tuesday is 1, etc. Then an int, or even a char, is sufficient to store which day it is in numerical form. Likewise, if we must store one of a choice of, say, 10 colors, we can assign numbers 0 through 9 to the colors, and then store the choice in an int. When you think about it, the ASCII or Unicode systems are doing the same thing. They're associating a series of integer values with a set, characters, that is not inherently numerical, and they're using a number code to represent each item in the set. Now, such an arrangement is called an enumeration. In a well-written enumeration, you declare a series of pound defines or constants rather than just using raw integers. So for instance, you might say pound define Monday 0, pound define Tuesday 1, or maybe const int black equals 0, const int red equals 1. You can do it this way in C, but C, like many other languages, offers a shorthand for setting up a series of integer constants as an enumeration. One might write instead, for instance, something like this: enum and Monday, Tuesday, Wednesday, etc. in curly braces. This will create 7 integer constants with values starting with 0 for Monday that you may then use in the program. Now, the enum declaration is more than just a constant creator. It's also a type declaration, somewhat the same way that struct and a list of fields is a type. Line 12 of list H declares an enum with just 2 options for which end of the list to add a new item to. But it also uses the enum to create a type def, list add type, which we use to declare parameter where down in the list add prototype below. Now, technically, a variable of enum type like this may only be assigned values from the enum list. In other words, where would be assigned only values list at start or list at end. In some languages, this rule is strictly enforced, but C, in typical fashion, will admit that a variable that stores an enum value is really just an int. And so you can treat where as an ordinary int if you like. The type list add type should be read as, this is really an int, but I plan to use it to hold values from a particular enum list. It's more advisory than it is strict enforcement. And the this is really an int bit shows most clearly in input and output. Let's look down at line 19 of list main.c here at the bottom. Sorry, 18. As you can see, we're using a %d format specifier to read where, which is a variable of list add type. And in the input, in the sample run down here, for instance, we have to enter these A calls. We have to enter a 0 or a 1. We don't enter list at start or list at end, literally. The same goes for printing enum type variables. You use a %d and you get the raw numerical value as output. So while the enum concept extends across dozens of languages, it's usually a very thinly disguised int, especially on input and output. Java, by the way, is a notable exception. It has a highly sophisticated object-oriented enum system, well worth studying sometime if you get into deeper Java. Now, all this said, it's still a good idea to use enums when you have a set of related integer constants, and to set up an enum type def to declare integers that store one of those constants. Another common concept in modern design, and doable also in C, is that of an iterator. In earlier lectures on linked lists, we had functions that looped through the list, for instance, printing all the items in the list. But each such function is of one purpose. It'd be useful to have some general way to loop through all the items in the list under the control of the caller, so that the caller can do to each item whatever it would like, perhaps printing them with a particular format or totaling them or some other operation. To do this with proper abstraction, we need functions that the caller can use to start an iteration, to test to see if the iteration is done yet, to retrieve each item in turn, and to advance to the next item. In our examples, these are respectively list start, list has next, list current, and list advance. These functions use and update the at field of the list struct. So list start, for instance, points at to the first node, if there is one. List has next returns true if at is not null, so we haven't run off the end of the list yet. List current, we'll get to the assert in a minute, list current returns the data that's in at's target. And list advance advances at to the next node. The field at thus becomes a sort of loop pointer, which we can initialize and advance via these function calls, as we do in the for loop on lines 27 through 29 of list main. Now, review the code for that loop and the for functions, and again ignore the assert calls for the moment, to be sure you see what's going on, and then answer these two questions. The first question, do this loop and the for functions work even on an empty list? What exactly happens if we run this 27 through 29 line loop on an empty list? Coming back from a pause, yeah, it'll work. List start, the call here, will set at to null immediately. And then list has next will return false, and the for loop will exit without even iterating. Here's question 2. Could I run 2 different iterations at once with this system, with the 2 iterations at different points in the same list? Coming back from a pause there, no, there's only one at pointer, so you can only be at one place in the list at a time. This second question shows a weakness of tracking an iteration via a field that's internal to the data structure, like at. The specific term for such a design is an internal iterator. There's a stronger external iterator design, and that provides a separate struct type, say a list iterator type, that has the at pointer. And you can create and use as many list iterators simultaneously as you like, each one representing a different point in the list. Details of external iterators are beyond this design discussion, so that's as much as we'll say here. Now, let's get to those assert calls that we skipped over. The 2 assert calls on lines 74 and 80 of list.c illustrate one of the most critical reliability tools in the C language libraries, including the file assert.h, as we do up here, gives you access to the assert function. Technically it's a macro, but we'll call it a function. You call this function passing it a Boolean test of any form that would be usable in an if statement. If the test is true, then the function returns without action and the program goes on. If the test is false, then assert immediately ends the program with an error message reporting the file name and the line number on which assert was called and the test that failed. This is far more useful than C's usual segmentation fault. You use assert to check conditions that should always be true and which represent a bug if they're false. Don't use it to check user input, for instance. The rule of thumb is, if this assert fails, I'll be modifying my code to fix a bug. But a bug can include misuse of a function. The contract for list current, as it says, and for list advance, requires that list has next be true, that add is not null. So it's good use of assert to verify this assumption and to report a error if the assumption is violated. That counts as a bug in the code. Learn to use asserts frequently. They'll save your life when debugging C code. Anytime you get a queasy feeling after some long sequence of logic and you're thinking, this is going to break, it's time for an assert, verifying any condition you think should hold at the end of your logic. Question 3, for example, follow the logic of the for loop in list drop here, this particular for loop, and write an assert regarding the state of prior and temp just after the end of that loop, which we might insert in here. The test should have two parts, ORed together. So coming back from what might be a lengthy pause there, a good assert would be something like this. The way the thing works, either prior ends up equal to null because the item we're looking for at toDrop is at the beginning of the list, and we never get prior changed. Or if we do get prior changed, then it should always be the node right before temp. So prior error next should equal temp. And that would then be a good assert check to make sure our loop had performed correctly.